Okay, our summary so far is with respect to the function from R2 to R. And what do we have? We have the gradient is defined to be gradient of f is equal to, it's a vector, it has fx and fy. So to help us think ahead, just remember that this is from R2 to R, and the gradient is a two-dimensional vector. So the dimension matches the domain. So this is 2D, so we think about it as a two-dimensional vector. And we think about it in terms of the mountain standing on the side of a hill, and then the gradient lives on the map. The map is a two-dimensional direction that tells you where to go. We have the directional derivative, dir, der, dir. And that's the derivative of f with respect to u, or in the direction of u. And then I guess on the quiz we had some issue here about being evaluated at a specific value, x, y, or a, b. And then we found this to be the gradient dotted with the u, provided that u is a unit vector. Dimension matches domain. So u is a unit vector. Again, I'm stressing the fact that this is all two-dimensional. And then we also found that another important property of the gradient is the gradient is a direction of maximum increase. It's a two-dimensional direction of maximum increase. And then we also note that the gradient is perpendicular to the level curve. Maybe I should have typed these things up. It's a lot of words to be writing chicken scratch and for you guys to understand. But, you know, it's like more than halfway through the semester. You guys can decipher my writing already, right? Only listen. It's recorded, so. All right. So can you tell that I was stressing the idea that this is in two dimensions? Because, why? Because we're going to take a look at gradients in three dimensions. So now we're going to consider functions of three variables. Now remember, a function of three variables is not totally out of reach for us. We took a look at level sets, or level surfaces we call them, by letting the output variable, sometimes we call it w, we let that equal to a constant, and then we have x, y, and z on one side of the equation equal to a constant, and then kind of brings us back to the quadric surfaces and stuff like that. So we can think about this as W as a function of x, y, and z, just so we get a semi-concrete visual of this. And we can, line by line, we can match it up with what's happening in 2 dimensions, right? So it seems pretty clear that if your gradient is the partials, the first order partials made into a vector, now your gradient for this is going to be the first order partials made into a vector. Only difference is that before we had 2 dimensions, we had 2 variables, independent variables. Now we have 3 independent variables. So this time we will have a gradient that is a 3-dimensional vector. So your gradient is going to be the derivative with respect to x in the first component, the derivative with respect to y in the second component, and the derivative with respect to z in the third component. This is a 3-dimensional vector. Okay. So we can also match it up with the directional derivative. We can have a directional derivative for functions with 3 variables. So our dir is going to be the derivative of f in the direction of u, and that's equal to the gradient dotted with u, except now u is still a unit vector, but now in 3D, is a unit vector in 3 dimensions. Oops. I had a color scheme going on here. All right, there's a couple of important properties that we saw with the gradients. So here we can still talk about the direction, except it's a 3-dimensional direction, but we could still talk about the direction of maximum increase. So a gradient is the direction, but this time it's in 3D. It's a 3-dimensional direction of maximum increase. It might seem hard to visualize, but we'll see if we can come up with an example of how this might work. So the gradient is a 3-dimensional direction of maximum increase. And then now this is the other interesting part that would help us look at tangent planes. A gradient is perpendicular to the level. Now, if we have a 3-dimensional domain going into a 4th dimension, when we set the constant or the output or the dependent variable equal to a constant, then we have a function of x, y, and z. Well, we have a relation of x, y, and z, and that describes a surface now. So a gradient is perpendicular to a level surface in 3D. Okay, so perpendicular to the surface will help us find tangent planes if we have a level surface. Okay, now let's see a little bit of this in action. Let's do some simple examples. So let's let t, capital T, equal to I don't know, 100 e to the minus x squared minus y squared minus z squared. I hope that's not too hard. We can take the derivative of this pretty easily, right? Okay. All right. So let's say this is our function. Now we could try to create some interesting scenario around this. Well, we'll do it some other time. But let's just say this is your function, and let's go through the steps of finding the gradient, finding a directional derivative, finding the direction of maximum increase, and stuff like that. So we know that the gradient of this one, so our gradient of t, is going to be just the partials of this thing with respect to x, and then with respect to y, and then with respect to z. So the partial with respect to x, this is 100, it'll stay 100. And then e to the minus x squared minus y squared minus z squared times the derivative of the inside quote is actually the power with respect to x. So negative 2x. Yeah. And then if you notice some symmetry around here, then you could probably figure out that the next one is the same. So we could just multiply that out. Oh, and there's a y. So if we're going to work with this a little bit deeper, we might want to factor things out so that we can have an easier thing to deal with. But I'm happy with this answer. But if you do want to factor out, it looks like we could factor out a negative 200 and then e to the negative x squared minus y squared minus z squared. And then after you factor all that out, all you'll have is an x, y, and a z. Interesting. So that's your gradient, written in a couple of different ways. So let's say we were at a specific point here. Do it. So we need to come up with a direction. U is the unit vector from 1 to negative 3 to 0, 0, 0. Now, if I connect this in three-dimensional space, this is probably not going to be a unit vector, so it'll be my task to make it into a unit vector. So what we need to do is, first of all, figure out this vector, what this vector is. So let's say V is a vector that connects from what to what. It's going to be head minus tail. So the head is the end point where you're going to end at 0, 0, 0, and then the tail is 1, 2, negative 3. So this is going to be negative 1, negative 2, positive 3. But then you want to make this into a unit vector, so we need the magnitude. Square root of 14. So 1 squared, 4 squared, 3 squared. Or 1 squared, 2 squared, 3 squared. So 1, 4, and 9. That's 14. So it looks like my unit vector is going to be 1 over square root of 14 negative 1, negative 2, positive 3. You don't what? I don't care too much about radicals in the denominator, so I don't care much about simplifying either. So this is what we have for our unit vector, and this is what we have for our gradient. The only thing left to do is we have to evaluate it at that specific point. So take your gradient and then evaluate it at 1, negative 1, positive 2, negative 3. So we need to square them. You get 14, right? So negative 200 e to the negative 14 times 1, 2, negative 3. That's the gradient evaluated at that point. And so to finally answer this question, your directional derivative in the direction of u is going to be negative 200 e to the minus 14, 1, 2, negative 3. And we're going to dot that with 1 over root 14, negative 1, negative 2, positive 3. And so remember the rules for the dot product. If you have scalars, you can just combine the scalars together and then just dot the actual dot product. So I have a negative 200 divided by square root of 14 times e to the negative 14 times, and then here I'll do the dot product, negative times negative, negative 1 times positive 1, negative 2 times positive 2, and negative 3, 4, and 9. So 200 square root of 14 e negative 14. So there was some simplifying that happened there, I guess. You have negative 14 in the numerator and square root of 14 in the denominator, then that's just negative 14 up on top. The negative from the inside of the parentheses will cancel with this negative from the 200. And then I think that's it. What? Yeah. So here's your directional derivative. So this is the rate of change as you go from one point to the other point. Is that okay? What? It's the rate of change. If you're here at this point, this will be the rate of change if you go towards the origin. Yeah, so but in 2 dimensions or 3 dimensions, the idea of a slope doesn't make any sense anymore. We'll just call it the rate of change. Yeah, so rise over run is only happening in something flat.
Yeah, you can't do that in 3D really.
Right, no.
So it's not like you're in space. So the gradient kind of substitutes that ideology?
Yeah.
Okay.
Maybe. Oh, think about this. Here, I have a scenario for you. Think about, let's say you're flying in space. And then the temperature in space is given by this function. So the temperature in space is given by this function. And so as you move in space in 3 dimensions from one point to another, your temperature is going to change because there's different temperatures in different parts of the room. So as you change, as you move from one point to another, you want to figure out how your rate of change, or what the rate of change of your temperature is as you move.
So are we in space or do we have time?
Well, you're in space. That marks the 3 dimensions, the x, y, and the z, and then the output is going to be your temperature. So if you're at the point 1, 2, -3, you can put 1, 2, -3 into the temperature function to figure out what the temperature is at that point. You could be in space too if you want, if you just put an axis there. Well, you can have temperature in space. Right, you get closer to the sun, it gets a little warmer, right? So yeah, this could be temperature. This could be something else too. I can't think of anything else, but it could be something else. It could be a density of something in space. Let's say you're swimming in hot chocolate. As you move along, there's a density of hot chocolate. If you go down further, it's a little bit more dense than if you go up on top. And so if you're swimming and you want to feel the density, how's the rate of change of density as you move from the top to the bottom and you start going down? So, I don't know. You can just make stuff up. What? Let's say you have weights on. All right. Let's keep going with this same example. I'm going to go to the next page. I'll take a picture of our function. And the next idea that we had was the maximum rate of increase. So let's say you're at a new point at 0, 1, 4. Find a direction of maximum increase. Okay? So we know that the direction of maximum increase is just a gradient. So it's just a gradient evaluated at this point. So direction of maximum increase is going to be the gradient evaluated at 0, 1, 4. So I think we had the gradient as -200 e to the minus x squared minus y squared minus z squared times the vector x, y, z. And then you just need to evaluate this at 0, 1, 4. And so we get 0, 1, 4, 0 for x, 1, so that would just give us minus 1, minus 16, minus 17. So negative 200 e to the minus 17, 0, 1, 4. Or you can distribute that negative 200 e to the negative 17 throughout the different components of the vector. So this is the direction that you would go towards. It looks like it's negative of the point. So it looks like if you just go towards the origin, that's where, if we're talking about temperature, that's where the heat source is, it looks like. All right. So now let's take a look at this as a level curve, or not a curve. Let t of 0, 1, 4 equals to t of x, y, z be a level surface. What did I just write? What's this? So remember, a level curve or a level surface is if you let the function equal a constant. If I put this point in, 0, 1, 4, into the function, I'm going to get a number, right? So what does that mean? That means t of 0, 1, 4 is equal to 100 e to the 0, 1, 4, negative 17 is a constant. And then if you let that constant equal to the function, you're going to have a surface. So 100 e to the negative 17 equal to 100 e to the negative x squared minus y squared minus z squared is a surface. Well, technically it's a level surface. That's a level surface to that function. Can anybody guess what this might look like? It looks complicated, right? But if you break it down, Jake said it was going to be a sphere. You guys agree? So, you know, if you cross out 100, take the ln of both sides, and then take the negatives out, x squared plus y squared plus z squared equals 17. So this is a sphere. And if you let the origin be like the heat source, like the sun, at each level, each spherical distance away from the sun, you'll be at a certain temperature, and then if you go farther away, your temperature is going to change to something cooler. And you keep going farther and farther away, you're going to get cooler and cooler. Yeah, it's temperature of the sun to the core, and so the temperatures of the sun on the outside, and then you start going inside, you'll have different temperatures. So anyways, this level surface happens to be a sphere if we really work it out. But let's say we didn't know and we didn't really care. And we want to find a tangent plane. Find a plane tangent to this level surface. At the point 1, 0, 1, 4. Sorry. So find a plane tangent to this level surface at 0, 1, 4. What do we need for an equation of a plane again? Normal vector and a point. We've got ourselves a point right here. What's our normal vector? The gradient, because the gradient's perpendicular to a level surface. And we happen to have the gradient figured out, evaluated at 0, 1, 4. So it's negative 200 e to the minus 17, 0, 1, 4. So if we want to find that plane, the equation of the plane, so it's just going to be this thing dotted with this thing, you know, whatever. So let's, you don't need to do this. I don't know why I'm doing this. Because all you need is anything that's parallel to this, so I can take out that constant out in front. Right? Because this vector here and this vector here is going the same direction, except this vector is longer, shorter, probably shorter because e to the negative 17. Yeah. So this will be shorter than it just had 0, 1, 4 is an equivalent normal. So we'll use this for your normal vector. And then we have this for our point. Now we got a point and a normal. And the formula says that it's just going to be 0 times x plus 0 or 1 times y plus 4 times z is equal to the dot product of 0, the normal, times the point, or dotted with the point. That's one way to get it, right? And then there's other ways to get it if you do some other stuff. So what is it? Y plus 4z equals 17. So that's your tangent plane at that point on that level surface. Okay? So we can take a quick look at the graph, since I think I could do this pretty quickly. That level surface, without writing it out like this, the 100 e to the negative 17 is equal to 100 e to the minus x squared minus y squared minus z squared. If you just write that as an equation, it's like an algebra equation, and cancel the 100s, take the ln of both sides, and then you get negative 17 equals to the negative thing. It really just boils down to x squared plus y squared plus z squared equal to positive 17, right? And then we have our point. Uh, 0, 1, 4. Where's the sphere? That one just barely missed. None of the sphere showing. This is supposed to be on the sphere. If I zoom out, I guess I can see it. All right. Huh. My tangent plane only has an x and a z, right? or y and a z. So that should be parallel. I was gonna, but I don't know if it's, did we do something wrong? All right, let's put the tangent plane. What is it? Y plus 4z equals 17. I guess. I doubted myself. What? What's so funny? What? What happened? Did I miss a joke? I don't want to miss a joke. Because I'm not what?
Let's say graduation.
Oh. That's lame. I didn't need to hear that.
We got about one.
Don't you have to pass this class to graduate?
Oh.
All right, let's take a picture of this because it looks like whatever. So we could see the geometry, a little bit of an application, and so the gradient is perpendicular to a level surface, right? And the gradient is perpendicular to a level curve. These two things down here at the bottom oh, I wanted that to be red. So these two facts in the bottom kind of give some idea of how to relate the gradient with a tangent plane. And we kind of had a handle on the gradient and the tangent plane for 2 dimensions. And so I want to just go back to this idea and see what's going on. And I don't want you to lose this idea of how to find the gradient for a function from R2 to R. Oops. I want a new page. So I want to just do a quick example of a function in x and y again. And let's do a simple example this time. How about an x squared minus y squared at -1, 2? Okay? So let's say we wanted to find the tangent plane at this point. And the gradient is only in 2 dimensions. 2x, minus 2y. Hey, yeah, that's the answer for your first problem on the quiz, huh? And then to help us find a gradient at the specific point, we evaluate this at -1, 2. So this is -2, positive -4. Right? Is that right?
Yeah.
Okay. No. Anyways, let's move on. To find the equation of the tangent line, do you remember how to do it? If you wanted to find a normal vector, this is 2 dimensions. How do you find a normal vector in 3D to find the equation of the tangent line? Or do you remember the other way we did it? No. This is where we depart from the quiz. Do you remember what we do? Isn't there a z is equal to f of ab? Remember that? What? Yeah, we could do that here. I don't know about easier, but there's another way. And wait. Well, it's perpendicular to a level curve, right? But I want a normal vector that's perpendicular to the surface. So our normal vector, remember I asked you to find normal lines a couple of times? What's the equation for a normal line? Or what's the vector for a normal line?
fx times x minus a plus f of ab.
Well, that's going on with the equation here. All right, well, let me finish this formula here. Fx ab x minus a plus fy ab. Oh, I'm not disappointed. Well, a little bit, but but the idea that this is a normal vector, right? And well, this is not the normal vector, but this is the equation for the tangent plane. This is the formula that we came up with. But I'm interested in actually just finding the normal vector, because I want to compare the normal vector. This is perpendicular to a level curve. This is perpendicular to a level surface. But we've dealt with this in 3 dimensions to find the perpendicular to a surface. There's a cross product of something. I don't want to do the cross product. I just want to get the answer. And so the normal vector is the answer that I want to get at. So we crossed 2 things. We got something. It would be, the way we crossed it, we got a... So the normal vector in general is going to be fx, fy, and, well, we had a negative and a positive 1, right? Or similarly, you can take away the negatives and then we would have a negative 1. So either of those normal vectors would work. So 2, 4. So 2, 4, and 1. If you took the negatives out. So negative, negative 2, negative, negative 4, and positive 1.
It's like you're adding a z term in there.
You're adding a z term, but what's the z term? 1. If
It's
so,
z minus.
but that's if you consider this to be negative fx, right?
Yeah.
So I want you to think about this this weekend. Think about how the normal vector for a level surface is different from the normal vector from a level curve. A level curve gives us a vector in 2 dimensions, and so you want to come up with a 3rd dimension to make it perpendicular. And that 3rd dimension is either 1 or negative 1, depending on how you approach it. All right? Cool. All right, so the extra credit will be due on Monday night. So Monday at midnight, if you want to. The comments on the thing. Have a good weekend.